Welcome back to the Deep Dive. Today we are looking at a paper that I think fundamentally reframes the architectural approach to large language models in software engineering.
It's a big claim.
It is. We aren't talking about prompt engineering or, just expanding the context window today. We are looking at the very structure, the representation of code bases themselves.
Which is a refreshing change of pace. I mean, we've spent the last year, maybe more, watching models get larger. But the fundamental problem of repository-level reasoning has remained remarkably stubborn.
That reasoning disconnect.
Exactly. We have these models that can generate fantastic localized code snippets, but they just fail to grasp the global semantic topology of a large, complex repository.
And that's the perfect entry point. The paper in question is titled Closing the Loop, Universal Repository Representation with RPG-Encoder, from Chengyu, Chengyu, and their team.
Submitted to Archive just this February.
And the hook, for me, is right there in the title, Closing the Loop. It's a really strong theoretical stance they're taking.
It is. They're essentially positing that repository comprehension and code generation aren't two separate, unrelated tasks. They're mathematical inverses of each other.
Okay, let's break that duality down, because it's critical.
Yeah.
The standard view is that generation is just mapping intent to implementation, right?
Correct. You can think of it as a probability, P of code given intent. You have a high-level requirement, and you expand that into concrete syntactic code.
But the authors argue that true comprehension, the kind an agent actually needs, is the inverse of that.
It's the compression. You are. On the one hand, you have your vector databases. They rely on dense embeddings, which gives you great semantic similarity. You can find code that sounds like your query.
But the vector space is unstructured. It completely destroys the topological information of the call graph.
It's gone. And on the other hand, you have the static analysis approach. So dependency graphs, abstract syntax trees, that sort of thing.
Which preserves the structure perfectly.
Perfectly. We know exactly what function calls what. But they're semantically sparse. An edge in a typical dependency graph tells you that a connection exists, but it has zero information about why it exists or what data is flowing through it.
So the reasoning disconnect is essentially an orthogonality problem.
Yeah.
We have semantics without structure or structure without semantics.
And that is the exact gap the RPG encoder is designed to bridge. They introduce this universal repository representation, and they're not just trying to parse code, they're trying to build a representation where the topology itself is informed by the semantic intent.
So let's walk through the architecture. They lay out a three-stage framework: encoding, topology evolution, and navigation. Let's start with that first one, the encoding. How do they actually construct this RPG, this repository property graph?
It's a fusion model. They basically acknowledge that neither ASTs nor LLM embeddings are sufficient on their own. So the RPG encoder constructs a graph where the nodes represent code entities, your files, classes, functions, and those are derived from standard static analysis. That gives you the skeleton.
But the real novelty is in the node features themselves.
Right. This is key. They don't just embed the raw code string, they use what they call lifted semantic features. The system performs a sort of localized inference step on each node to extract its latent intent.
So what does that look like mechanically? If I have a function, say process transaction, the node in this RPG isn't just the text of the code.
No, it's a high-dimensional vector that encodes something like handles payment gateway logic, requires a valid user session, modifies the ledger state. It's the functional summary.
And these semantic features are then fused with the structural edges.
Exactly. This creates a graph where the distance between two nodes reflects not just the call stack depth, but their actual semantic relevance. It aligns the structural map with the conceptual map of the codebase.
Okay, but that sounds computationally very, very expensive. And this brings us to the second mechanism, which I think is maybe the most significant engineering contribution here: incremental topology evolution.
This is the absolute make-or-break feature for any real-world deployment. I mean, anyone who's worked with graph-based RAG knows the scaling issue. If you're indexing a monorepo with millions of lines of code, building that graph is a huge operation.
It's an O of N operation, where N is the size of the whole repository.
Right. And in a CI/CD pipeline, or even just an interactive coding session, the code is changing constantly. If every single commit forces a full re-indexing of the entire graph, the latency is just unacceptable.
You can't have your AI agent pause for 20 minutes to reread the repo every time you save a file.
You can't, and the authors claim a 95.7% reduction in overhead compared to traditional graph baselines. It's a massive number.
So how are they achieving a reduction of that magnitude?
By moving from O of n to O of delta, they've completely decoupled the maintenance cost from the total repository scale.
So they're just isolating the subgraph that's actually affected by the change.
Precisely. When a change happens, say a modification to some utility function, the RPG encoder identifies what they call the impact subgraph. It calculates the propagation radius of that change and only re-encodes the semantic features and edges for that modified node and its immediate dependencies.
That's very elegant. It treats the repository representation as a dynamic system, not a static snapshot.
It's a continuous state update. That's why they use the word evolution. The topology evolves in lockstep with the codebase, which ensures the agent is always reasoning over the current state of the logic without that massive computational penalty.
Okay, so we have a dense, semantically rich graph, and we have an efficient way to keep it updated. The third pillar is navigation. How does an agent actually query this structure?
This is where we really move away from retrieval in the, traditional sense. Most RB systems are using similarity search vector dot products to just grab the top K chunks.
But the RPG encoder uses what they call structure-aware navigation.
It actually traverses the graph.
Right.
It creates this unified interface for the agent. And because the graph encodes both structure and semantics, the agent can perform hierarchical localization. It can start at the repo root, query the high-level module intents, and then traverse the edges down to the specific function or variable it needs.
Which solves the fine-grained localization problem.
Yeah.
Instead of just hoping a vector search lands you in the right file, the agent is systematically narrowing the search space based on the actual logical architecture.
It's deterministic navigation, but it's driven by semantic probability. It's basically mimicking how a senior engineer navigates a new codebase, right? You start with the folder structure, and then you drill down based on functionality.
Let's pivot to the empirical evidence then. All this theory is great, but does it actually improve performance on standard benchmarks? They tested this on SWE-bench Verified.
Which is really the gold standard for this domain right now. We're talking about resolving real-world GitHub issues, and the metric to watch here is a C at 5 accuracy in the top 5 predictions.
They reported 93.7% SEC at 5.
Which establishes a new state-of-the-art. But, for this audience, we should contextualize that number. Achieving over 93% on retrieval for these repository scale contexts, it implies that the reasoning disconnect is, for the most part, bridged. The system is almost always finding the relevant context.
But the static benchmark isn't the whole story. They also included results for something called SWE-bench Live Lite.
And this is vital. Standard benchmarks are static. The code doesn't change while the agent is working. Live Lite actually introduces dynamic code changes during the evaluation.
An RPG-encoder outperformed the best baseline by over 10%.
And that 10% gap is the direct result of the incremental topology evolution. Other models were likely suffering from stale representation. They were reasoning on an outdated map of the code. RPG-encoder just adapted in real time.
It proves the robustness.
Oh.
But I really want to spend the rest of our time on the third metric because I think it's the most theoretically significant, the reconstruction test on RepoCraft.
I agree completely. This is the information theoretic proof of their entire core thesis.
They achieved 98.5% reconstruction coverage. Let's unpack the methodology here because they're not just solving bugs, they're testing the compression algorithm itself.
Exactly. You have to go back to that inverse process paradigm. Comprehension is the compression of implementation into intent. So to prove they've achieved a universal representation, they ran a round-trip test.
They encoded an entire repository into their RPG format, threw away the original source code, and then asked the model to regenerate the repository using only the RPG representation.
It's essentially an autoencoder, but for whole codebases. If the representation was lossy, if it only captured keywords or file names, the reconstruction would completely fail. You'd get hallucinated code that maybe conceptually matches, but is syntactically or functionally broken.
But to get 98.5% coverage means that the RPG retains incredibly high-fidelity information about the implementation details.
It implies that the lifted semantic features and the topological structure constitute a nearly sufficient statistic for the entire codebase. The representation mirrors reality so closely that you can invoke the process and get the code back.
Which validates the whole closing the loop title. If you can generate from the representation, then the representation is a valid compression of the code.
And that has massive implications that go way beyond just fixing bugs. If you have a high-fidelity, manipulatable representation of a code base, you open the door to high-level architecture manipulation.
Right. We're not just talking about code completion anymore. We're talking about automated refactoring, architectural migrations, managing technical debt.
Exactly. If the agent understands the dependencies of intent, not just calls, it can safely refactor a core module, knowing exactly how that change will propagate semantically through the entire system. It moves us from patching agents to maintenance agents.
I think that distinction is the key takeaway. A patching agent uses local context to fix a syntax error. A maintenance agent uses global context to evolve the system's architecture.
And the RPG encoder provides the data structure needed to support that global context and to do it efficiently.
To wrap up, if we look at those efficiency metrics, again, that 95.7% overhead reduction, it really seems like this is an architecture that's ready for integration into, say, standard IDEs.
Oh, I would absolutely expect to see this logic integrated into the next generation of language servers and Copilot-style tools. The ability to maintain a live graph of the repository on a developer's local machine without eating all the RAM is the prerequisite for having truly local, autonomous agents.
It really does feel like we're approaching a point where the distinction between, writing code and maintaining the topology of that code starts to blur.
Yeah. In a way, yeah. We're sort of moving back to the old ideas of model-driven engineering. But instead of a human manually drawing UML diagrams, we have an AI evolving a probabilistic graph in real time. The map and the territory are converging.
A fascinating convergence of graph theory, software engineering, and generative AI. For listeners who want to dive into the specific loss functions they used for that semantic lifting or the graph traversal algorithms, I highly recommend reading Closing the Loop, Universal Repository Representation with RPG-Encoder.
The section on their topological update algorithm is particularly rigorous. It's really worth your time.
Thank you for joining us on the deep dive. We'll continue to track these developments in what you might call neural software engineering.
A pleasure to be here.
Until next time.